All right, yeah.
So I had a question for this program. I noticed because it's a script and not, a compiled file. Mm-hmm. The whole thing works and it can check for everything. But if you put in strings when it expects an integer for a loop that's going on, it'll spit out error codes and continue. Is there any way to prevent that from happening?
So is this like when the user puts in?
Yeah, if it requests a user input for something that uses a loop for integers.
Yeah.
And in one very specific case, if they put in characters instead, the program will continue going, but it also spits out the error code saying, I expected a number here, not a letter.
It prints that out?
Put something in that's right, but it'll still put out the error codes, which you wouldn't get.
But are you still using that variable to? So yeah, so it shouldn't be giving you error codes. So let's try this. Right, so something like that. All right, so if you loop 3 times, that's my bad. I'm new to this. All right, so forgot to increment count. All right, so 3 times it says loop 3 times. If you say hello, right, you should be able to detect that that's not a number without generating an error message.
I have a situation kind of close to his.
Okay.
I'm a person who uses the number pad on the right side quite often, and it seems like PuTTY or something like that doesn't read it very well. It reads it as arrow commands and all that.
Mm-hmm.
And when I accidentally do it and I quickly press enter, it reads it, but not as a character. Could you try with that maybe?
So when you hit a thing on the keypad and it's not sending it as a number, it's sending it as an up arrow or something like that, then you got all kinds of weird characters. You got escape characters and things like that. And this trick for detecting an integer won't work for that.
Okay.
Right, so that will give you an error message most likely, but I'm not going to check that. So like that, right?
Yeah.
That'll mess it up, but that's why I said it's either going to be a number or it's going to be like a word, a bunch of letters. And as long as it's one of those, right, that check for $num times 1 equals $num should catch it. And you exit at that point, or you put that in a loop and keep asking until they put in something that's an integer.
Yeah, it was, I don't know, I guess for the actual check, if you put yes, if you put no, and for everything else, that works, but that's within a bigger loop.
Okay.
And that bigger loop uses a similar variable that's read from that yes, no.
Okay.
Input, and then, or not the yes, no, but the stick input, and if you put a value of a letter for the stick, then it'll...
You should never get to that statement at the beginning of your while loop in that case.
Okay.
You should either exit the program or go back and get another entry until it's an integer, whatever part you're in.
It's just strange because it doesn't break the program, it just says...
Yeah, so, but there's a lot of cases where bash will keep running and not necessarily do the right thing. So if we comment out that exit, right, and we say loop, and we say hello, right, it'll tell us not a number. Well, it exited anyway. Right, because in this case it turned it equal to 0. But there's other cases where it might just go ahead and run with that 0, and then it'll keep executing your code and do something weird.
All right.
If you want to show me your specific case, we can like drill into that also.
Okay.
Yeah.
I have a sort of random question regarding the next program assignment.
Okay.
It says submit your final.tgz files via Canvas. What's the difference between TGZ?
That might be a
and
typo.
R files?
Might be a typo. Let me look. But I didn't put it in there. I put it on here. Hey, you got 59 submissions. That's better. All right. So, for this assignment, yeah, I want a TGZ. So, you're going to use the following commands: tar, cvf. Do I tell you what to call this? You can call it whatever you want. So, I don't know. I'm just going to call it pa2.tar. And I'm going to submit stick.c. And you may have this program split up into multiple files, right? Depending on how you want to write this in C. And we'll talk about modularization a lot for this assignment. You may have one big long main program that's 80,000 lines long, right? Or you may have a main program that calls some other programs, like you might make a separate file that prints out the number of sticks. And you put your function in there and then you just call it. So you might have other files in here. But whatever your list of files is that make up your project, right? You list all of those after the name of the archive. And this creates an archive, pa2.tar. Okay, so the other thing you're going to do is you're going to use the gzip command. You just say gzip pa2.tar, and that gives you a pa2.tgz. Or maybe it's a tar.gz.
Did you say that's gzip?
That's gzip. And then rename that to pa2.tgz. So let me show you what that looks like. All right, so let's say that your submission consists of main.c, main2, main3, and main4.c. Okay, and you want to make all of those together. So I'm going to say tar create verify file pa2.tar main.c, main2.c, main3.c. Okay, because that broke my program into 4 pieces. So it adds all 4 pieces to my tar file, and now I've got this new file, which is pa2.tar. And that's what you submitted for PA1, okay? So there's one more step for this one, gzip pa2.tar. And now when you do an ls, there's a pa2.tar.gz. Okay, that tells you it's gzipped. And the last step is to rename this, so use the move command, pa2.tar.gz, pa2.tgz, which is sort of the standard abbreviation, the standard extension for a gzipped tar file. So now I've got a pa2.tgz. That's what you can upload to Canvas.
If you give tar the Z
Yes.
switch, then it'll do it.
It will do it for you. But I want people to do this because I want them to know both tar and gzip. So, but yeah, if you're familiar with that, you can put a switch on tar. All right, so 3 steps. Do your tar to create the tar file, do gzip to create the .gz, and then just do a move command to rename it to tgz. And again, do this sooner rather than later. You can do this right now. You can make a dummy project, make some empty files, tar them, zip them, rename them, upload it to Canvas. And if you can't do that, if you can't figure out how to do this, Canvas won't let you upload it, right? So you'll know something's going wrong. And once it's uploaded to Canvas, you can go to Canvas, you can say download my submission, you can rename it to a tar.gz, you can say g-unzip, and then you can say tar xvf, and you can pull all these files back out. And know that you've got this process of upload and download totally nailed, right? You can do that today, and then you don't have to worry about it 2 weeks from now when the deadline's coming up.
You said g-unzip?
Yeah, so the way you undo this, you don't really need to rename it, but rename it to .gz, and then do g-unzip. You get back to pa2.tar, and then do a tar xvf, and that gives you back your original files. And there's always questions on the midterm about the tar command and the gzip command and the g-unzip command, right? So if you're using this enough, you don't even have to study that when it comes time for the exam, right? Because you've been doing these things for every assignment, or maybe to make your own backups and stuff, and you'll just know what these things are. All right, so other questions? Yeah. So let's talk about PA2. The short answer is I don't necessarily recommend multiple files, but I definitely recommend multiple functions. Okay, and this we didn't talk about for Bash because Bash doesn't always make that easy. So let's look at PA2 first of all. PA2 is the same basic behavior as PA1. It's the stick picking game with the following changes. Program must be written in C. Okay, it's a C programming assignment. The user always goes first, so you don't have to do the user computer thing this time, okay? User always goes first. The user might enter anything, okay? This could be integers, this could be a blank line, this could be a $sign followed by a comma, could be anything, okay? This is the cat walking on the keyboard thing. But we have the power of scanf now to help us figure out is this an integer or not. So arbitrarily badly behaved behavior. The number of sticks you want to play with can be specified in two ways. You can run the program with a command line argument. If you say PA2 space 25, you're playing the game with 25 sticks. If you just say PA2, the program has to say how many sticks do you want to play with. And the user types in a number, and you got to error check the number again. I don't think I put a minimum number of sticks, so if they want to play with one stick, that's fine. And in this case, if there's an error in choosing the initial number of sticks, game's over. Okay? So PA1, you had to keep asking. PA2, how many sticks you want? They say, ha, game's over. Okay, they're not playing. All right, and then as you're playing the game, every time the user enters how many sticks they want, right, they have to type in a valid integer. And it's got to be between 1 and 3. And in this case, if they put in a bad entry, don't exit, just keep asking them. Okay? The only time you exit immediately is if they put in a bad number of sticks to start with. So it's sort of the opposite of PA1. And you got to use scanf to test the number of sticks that they want to take. If you use A to I, if you parse the ASCII codes, things like that, I will find a test case that makes it break. Okay, almost guaranteed. So use scanf and ask if you don't know how. So same gameplay, right? Same algorithm for how the computer should try to win. Try to make the number of sticks multiple of 4 when it's the user's turn.
So it's not going to make the user lose if they type in 2 things wrong?
Nope, just keep asking them. Right? Once they're playing, they're committed. They can't leave. Bishop of battle. Yeah.
So it's not the same algorithms, as linguistic,
%4. Yeah, same algorithm. Right? So if there's n sticks left and it's the computer's turn, look at n mod 4. If it's non-zero, that's how many sticks you take. If it's 0, take 1 stick. And then just continue until there's no sticks left. Whoever took the last stick wins the game. All right, so that's the basic setup. let's talk about modularizing code. So modularization is the idea of breaking your code into pieces. And here's one way to think of this stick picking game. First, there's some initialization. We're asking how many sticks, we're asking, well, we're not asking who goes first, but mostly we're asking how many sticks we want to play with, and we're setting up some internal variables or something like that. And then we do the following. So the user takes a turn, the CPU takes a turn, and we go back to the top. Right. And then at some point we exit this loop and the game's over. So there's only 4 things our program has to do. Some sort of setup in the beginning. Do whatever you have to do for the user to make a move. Do whatever you need for the computer to take a move. And then when there's no sticks left, the game's over. Do whatever you have to do to announce the game's over, say who won, right? I can write this in 4 lines of code, okay? But those lines are going to be something like a function call which says, do my initialization, do the CPU turn, do the user turn. And this might be a while loop that says something like, while the number of sticks is bigger than 0, do the user turn, do the CPU turn. And then when we're done, do whatever we need for the game over. So your main program can be very, very short, right? But it's not just a bunch of C statements, it's really a bunch of calls to these functions that are doing very, very complex things, right? So what does this user turn function look like? Well, you know,
It's a while loop that asks for a number.
yeah, so ask the user for the number, see if legal, and if it's not, go back up here, and then subtract from the pile, and then show the pile of sticks. And I'm not going to write the code in here to show the pile of sticks because I know in the CPU turn I also have to show the pile of sticks. And I know in the initialization when you tell me how many sticks to play with I need to show the pile of sticks. And I don't want to write that code 3 different places. And more importantly, I don't want to have to change it 3 different places if I find a bug or if the specification changes. So I'm going to write that once in another function called showPile. And I'm just going to call it here. And then I'm going to actually call game over in here. Because the game might end after the user moves or it might end after the CPU moves. So at this point I'm going to say, you know what? I want to check if game's over after each player takes their turn. So I'll call game over in here. And that's pretty much what user turn's going to do. And game over is going to say, you know, how many sticks are left. And if it's 0, then say, you know, the game is over. And tell who won. And I don't know, you might record the scores in a file or something if you were being super fancy. And then you just exit, right? So game over, I'm going to have to tell it some arguments, right, which is like the number of sticks. And I need to tell it who's just took sticks from the pile, so I might send it a character like you. And then inside game over, I basically say if number of sticks is 0, then print out a message. If this argument was a U, say, hey, you won the game, congratulations. If this character was a C, say, hey, I won the game, you know, I'm great. And in CPU turn, I'm going to do a bunch of stuff, but at the end I'm going to call game over. I'm going to pass an argument of number of sticks and a flag so that the game over code knows that it's the computer who picked up sticks last. And in game over again, if number of sticks is 0, it'll check this, and if it's C, it'll say, hey, I won the game. So this is modularization. This is breaking your function, which is to play the stick picking game, into smaller functions, which is do some setup, let the user take a turn, let the computer take a turn, and to break those into smaller functions, which is get a legal move, subtract it from the pile, show the pile, see if the game's over. And this stuff up here, ask user for a number, see if it's legal. If it's not, remind them what the choices are and ask again. That's going to go in here. It's going to go in CPU turn. Let's modularize that. So we can write a function which is get user move. And maybe this is going to return an integer. And that integer is going to be a 1, 2, or 3. That tells me how many sticks the user wants to take. And inside here, I'll say, prompt the user for input, read a number. If it's not a 1, 2, or a 3, remind the user and go back up here. Otherwise, just return whatever number they entered. Okay, so why do we want to do this? There's a few reasons. One, it lets you write your main program in about 10 minutes, maybe 5 minutes, right? Because your main program doesn't really do anything. It's really just kind of an outline of what your program is. You're deferring the actual hard work to all of these other functions. Okay, but it gets you away from the empty screen, and the empty screen can be terrifying, right? Because you look at the assignment and it's got all these words and stuff, and you've got memories of PA1 in your head, and now you're in VI and you're looking at the empty screen and the blinking cursor. What the heck am I going to type, right? Well, this gives you a whole main program, right? So it gets you past, the empty page thing. It lets you reuse code. So this code that's showing the pile of sticks, right, I can just pop into all these other functions. But the most important benefit of modularization is it lets you develop your code in small pieces. So I don't know how I'm going to do any of these things, but I got a pretty good idea how I'm going to do this show pile function, right? I'm going to write a function called show pile. It's not going to have to return anything, so it's going to be void. And it's going to take one argument, which is how many sticks I want to print out. And we could do something like this for integer I equals 0, I less than n, I plus plus. Print out a pipe. And if this doesn't occur to you pretty quickly, right, go back to your 121 notes, and you've definitely done stuff like this in 121, right? We want to repeat some statement n times. This is sort of the standard for loop for it. Just iterate from 0 and continue while you're less than n. And then if we want to print out the number n in parentheses, just print a parenthesis, a %d, a parenthesis, go ahead and throw a new line there. There's the whole show pile function. You don't have to write it like this. There's other ways you can write it. You want to put some comments in here. We'll talk about that in a second, right? But there's my show pile function. I haven't done any initialization, user turn, CPU turn, modulo 4, none of that business, but I've got one of my functions written. And I can make a main program, and I can say show pile 5, show pile 20, two-line main program, compile that up, link it with this, and run it, and I should get 5 sticks with a 5 in parentheses. I should get 20 sticks with a 20 in parentheses. And now I'm done with this, right? So I sign off on this. I don't have to look at this again. It's done. And when I'm writing my user turn and my CPU turn, I can just treat this like any other function in C. I can treat it like printf or square root. Oh, here's a function that prints out a pile of sticks with a number in parentheses at the end. Right? So you take your problem and you pull off a piece of it, you code that up, you test it, and now it's just another function that you have at your disposal. And now when I'm writing the user turn, I don't have to think about that, right? And I can do the same thing for this. I can write my getUserMove function, and I can test it with a main program that just says, you know, integer I equals getUserMove, and then print out the value of I. And when I run that, I can keep typing in garbage here, and it should keep reminding me what the choices are. And when I type in a 1, 2, or 3, it should return that value, and my main program should print out 1, 2, or 3. And so now this is done. You can sign off on that. And now I've got 2 big pieces of the user turn totally under control. Right? So the other end of the spectrum on how to do this is you sit down and you say integer main paren curly bracket, and you start writing 80,000 lines of code in your main program. Right? And sometimes that's fun under certain circumstances, but it's usually not fun in a class, right? Because it's usually not going to work. There's going to be an exercise in debugging and frustration. So modularize, right? This is going to be a key theme throughout this course. I'm going to keep saying this again and again. Break your code into small pieces, develop each piece one by one, test it by itself, and then use it to build up the more complex pieces. And at the end, you know, you've got all of these things written, and you write your main program, and it's like, well, I already wrote it. It was just calls to these 3 or 4 functions, and we're done. Okay, you don't need to modularize it into these modules. This is just an example. Okay, again, you need to find what makes sense for you, what's sort of the way that your brain thinks about this. Okay, but I'd like you to explore the areas of that that relate to breaking things into functions. And see if you can find a way that makes your life easier. All right. Questions about that? Yeah.
Are we going to talk at some point about header files and breaking it into multiple programs?
Yes, and we're also going to talk about make files, which is how you put those multiple pieces together.
I tried messing with that myself. It worked.
It's quirky, and it's a little quirky in C because you have to use like extern statements sometimes. Mainly, you just have to do function prototypes. And as long as you're not using global variables, and usually you want to avoid global variables, okay? So outside of your main program, in the very beginning, before you say main, you can declare variables, and those variables are accessible everywhere. It's probably best to avoid that, okay? When we call a function, we can pass arguments to it, right, like down here, and that's really the right way to pass information around. Global variables occasionally make sense, but they're usually considered kind of sloppy. And if you think you have a case where you can't pass things around and a global really makes more sense, come and talk to me and let's see what's going on, because it might be one of these use cases where that's the best approach. But as we move through this sequence, when we get into 222 in winter, which is going to be more C, but it's going to be object oriented, right? Or it's going to be data structures. This is going to be essential, right? We're really going to have to work with modules. And then when we move into 223, which is object-oriented, right? Everything is based on this idea of breaking up functionality, breaking these things into little pieces and putting these pieces together. And it's all about code reuse, about not reinventing the wheel. So there's a piece that does almost anything you want to do. And an object-oriented language makes it very natural to sort of put those pieces together. So this is all kind of practice and lead into where we're ultimately going in spring, which is Java. All right, other questions? So my plan is to grade PA1 over the weekend, and I'll give you feedback on it. But then Monday we'll talk about it in some detail. Okay, any things that I see recurring in different people's submissions, or anything that I think I didn't go over appropriately. We'll talk about all that on Monday. And I can show you my version of PA1 if you like that also. But I'll definitely try to get them graded over the weekend, probably sooner rather than later, I hope, but we'll see. All right, anything else? So let's talk a little bit about Git, because I've been saying we're going to do this. So how many people here have a GitLab account? All right, log on to GitLab, get yourself an account if you want to do this. Not right now, but you know, over the weekend. So there's some one-time setup stuff you have to do, okay, to make Git work. And some of this you only have to do one time when you start using Git. Some of it you have to do one time when you start a new project, okay? And then there's some things you have to do every time that you make a change. So the initial setup is basically getting a GitLab account, okay, which you do by going to their site and signing up, responding to the verification email. And then you have to set up some authorization between whatever machine you're using Git on, which could be the server, could be your laptop, could be both. You have to set up an authorization between that and GitLab. And the idea is you don't want to have to type in a username and password every time that you want to access your files. So you set up a secure handshake between your machine and the remote system. And the beginning of these instructions basically tell you how to do this. And they basically refer you to documentation inside GitLab. I hope I'm logged in. I've got a feeling I'm not. I don't even have a network connection. That's not GitLab. That's GitLab. Hold on. All right. So this is what GitLab looks like, right? You have a list of projects, information about when they were last updated, and so on. Let me start a new project over here. So this is going to be new 224A project. The description will be haha. Make your project private, right? Unless this is something you're collaborating with somebody, make them private for this course. So it gives you a set of quick instructions to get you started. So the one-time thing you have to do is these two Git Config Commands. Okay, this is once per machine that you're using GitLab on, not once per project. So git config -- global user.name, and you want your username and then user.email, and this is whatever you put in when you set up your GitLab account. Okay, that identifies you. There's also let's see if I can find it really quickly. If not, we'll do it later. I can't find it right now. So what we'll do Monday, if if it works, is we'll have somebody come up here with a new GitLab account and do this, right? Because I don't want to create a new account for myself. But you'll basically go through some instructions to set up this secure ID, and you basically you do a command SSH keygen, you copy it into a particular file, you copy the public key and you paste it somewhere on GitLab, and it just sets up a handshake, okay? And then you can access your repository without having to put in a username and password. Also, one-time setup, if you want to use VI, you can set that up as a default editor for making comments. All right, so you're sitting on Unix, and let's go into a new directory. So I'm in this new project directory, and here's file 1, and here's file 2. So I got 2 files in my project. Okay, so do you know ls-a? It says show me all the files, including the hidden ones. So you've always got dot and dot dot. That's your current and parent directory. That's all I've got in here, plus my 2 files. Okay, so you run some special commands. So the first one is git init. This initializes a repository on your local system. And you do this once per project. So I'm in a new directory. I've got some files. I want to use git to maintain my files. So I say one time git init. And now I've got a new directory called .git, a hidden file. Don't ever mess with that directory, okay? You mess with it, you break it, your Git repository is hosed. But it's got stuff in it, okay? But pretend it's not there, so if you do an ls, you don't see it. Okay, so I've got my files. I want to put these into my repository. Here's what I do. I say git add file 1. And it does what's called staging that file. Okay, it moves it onto an area called a stage, I guess, and says, okay, I'm going to add this file to my repository. It doesn't actually add it. It marks it as something I want to put in the repository. And I can say git add file 2, and now I've got 2 files staged, ready to be loaded into the repository. And I can say git status, and it tells me I've got 2 files. File 1 and file 2, they're both new, and it says no commits yet. Okay, these are changes to be committed. Committing means taking these things I put on the stage, put them in the repository. So we don't put files directly in the repo, we move them to the stage, and then we take everything on the stage, dump it in the repository. So it lets you put things on there and say, oh, I forgot file 3, I didn't want file 2, and so on and so forth. Okay, once everything is on the stage and I'm ready to commit it into the repository, it's git commit. And it brings up, in this case, VI, because I set my editor to VI. If you don't do that, it brings up Tico or Pico or something, another editor. And it says, please enter the commit message for your changes. Line starting with a number sign will be ignored. And everything here has a number sign, so this is not going to show up in my file, okay, in my repository. But I can put a message in here saying something like initial version of super duper code. And I'm just going to save that, and that's it. So my changes have been saved in the repository. Now I don't see that anywhere, I just see file 1 and file 2. But under this .git directory, there's stuff. And somewhere in that stuff is the current version of file 1 and file 2, and this message, initial version of super duper code, and the date, and some checksums, and a whole bunch of other information. And somewhere down the road, if I want to get back to this version of file 1, file 2, I can do that. There's Git commands for pulling things out of the repository, copying them out of the repository. In general, once you put something in a repo, it's there forever, okay, unless you delete the project. You can delete file 1, and it'll disappear from this directory, but the old version of it is still there in the repository. Okay. You can make changes to files. You see the new version here, but the old version is still available. So that's the basic use of Git. And by and large, it's sort of a one-way process at this stage. We push things in the repository, but we're not really pulling them out. We're using it just as kind of a local backup. Okay? but the backup is in this directory. It's, you know, this home directory 224 new project and this .git subdirectory. So that's the first version of Git, and that's not a bad practice just to do local backups. But if I do this on my laptop, my backups are here. If I do it on a Linux server, my backups are in the Linux server, and they're two totally separate repositories. Okay, if you want to use Gitlab, which is the cloud-based service, that's where these other instructions come in. So, create a new Gitlab repository from Linux. So I've already got a project going on Linux, and it's called new project. So let's go ahead and push this over to Gitlab. I'm playing without a safety net now, so be prepared for whatever happens, because I haven't tried this ahead of time. Okay, so I'm sitting in the directory where new project is, and I'm going to say git remote add origin git at gitlab.com colon, and I think my name, I don't know what my name is, I think it's Nick Macias, uppercase, slash, and what should we call this repository? Should we just call it new project? We'll call it ha ha ha. I'll use 4 ha's because I probably have a ha ha ha. Okay, ha 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 dot git. Let's see if this works. Okay, and then we're going to say git push origin master, git push dash u origin master, because we already did this adding and committing of our files, right? So we just want to push our repository over to there. Let's see if this works. Looks pretty good. All right, so let's come over here to Gitlab, and let's look at our projects. And let's look at your projects. And there's ha 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 ha. And if I click on that, I'm looking at that repository. There's my last commit, initial version of super duper code, and here's file 1, and it says haha, and file 2 is an exact copy of that. So file 2 is ha ha ha. And it's like tucked away safely in the cloud. Now I come back here and it's like, oh, I just figured out how to do file 2. Should be ho 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 a whole bunch of times. All right. So I want to push that change into my repository. So git add file 2, git commit, add the new version of haha, git push origin master. So now if I come over here and I'll just refresh this page, the last change was add a new version of haha 20 seconds ago. And if I look at file 2, that's got my new code in it. But I can also go back and I can look at the older version of file 1, but we're out of time. So that's the basic stream, right? And then the other side of it is I can go to another machine and I can say pull from that repository to a local repository, and I can make a clone of this on, say, the Linux server. And now I can keep these in sync. But to do any of this, you got to set up a GitLab account, right? Do the one-time init with the git config for your username, email, and editor. And then you got to set up the SSH key, and it'll give you instructions for that, okay? But Monday I'll ask for someone to guinea pig themselves, and we'll go through that in their initial setup as a demonstration.